those things also we did it. So let us compute again. Probability that half less than x less than 0, half less than y less than 0. So basically this is in this region, suppose this is the region, we have to do this probability density function dx dy. Now the dx dy, it is actually not all the place it is non-zero. So this is suppose 1 0, this is 0 1, this is 0 1, and this is become 1 1. Now this is the line y is equal to x. This is the region where it is non-zero. Now we have to find what is the probability up to this is half 0, and this is 0 half. Now here so this region is this is non-zero in this region. So fxy xy is non-zero when 0 greater than y less than equal to x less than 1. So here you can see this joint here, 0 less than y less than equal to x less than 1. So if you do first the integration, let us do first dy dx. So you change the order of integration. So assuming that this can be done because it is finally exist. So in this region, so then it is very simple that y limit is 0 to x and 0 to x. Whenever x is 0 to half, y limit is 0 to x for when whatever. So y limit becomes 0 to x, y equal to x, this line. So then just we compute it. So this value actually nothing but k is 2 here, 2 dy dx. So this is 0 to half, this is 0 to half 2x dx. Now x square by 2, 2x square by 2, 2 to cancel, 0 to half, this is nothing but 1 by 4. So this probability 1 by 4, earlier also we computed, I can remember this value, it came 1 by 4. Find the conditional probability density function y given x. So before for compute the conditional mean, we need the conditional probability density functions. So then how we can find the conditional density function? So the conditional probability density function, the probability density function of suppose y given x is equal to x. So this definition is y given x is, this is joint probability density function by fxx. So now this joint probability density function is this is non-zero in this region, 0 less than y less than equal to x less than 1, and fxx also non-zero whenever x is between 0 and 1. So for a given x, for x belongs to this open interval 0 1, so f of y given x can be written as this is f of xy is nothing but 2 by f of xx is we have found 2x, this is 2x, and whenever range of y is here, if you take the intersection of both this range, then y is less than equal to x less than 0. So this is nothing but, if you cancel this, otherwise it is 0. So we can write whenever x is here, we can write x between 0 1, then only this value, otherwise 0. So we can just finally we can write 0 otherwise. So for x belongs to 0 1, this value is 0. So this is nothing but, it is a uniform distribution, 0 less than y less than equal to x for a particular value of 0 1, and this is 0 otherwise. This is the conditional probability density function of y given x. Hence we can find the conditional mean. So hence the conditional mean of y given x is equal to x. Conditional mean of y given x equal to x is, so the definition is y given x, so expected values of y given x, this is minus infinity to plus infinity y f y given x dy. So this is the definition. Now this is for a particular value of given x, this is distributed as 0 to x, 1 by x. So this is non-zero, 0 to x. So this is nothing but 0 to x, and this is y, and this is 1 by x dy. So then you will find this is nothing but 1 by x here as a constant. So for actually x is given value, so x is between 0 to 1, so then 1 by x, actually x is between in the open interval, so x cannot be 0, x is greater than 0, so 1 by x, then y square by 2, and limit is 0 to x, so x square by 2, 1 by x into x square by 2 minus 0, so 0, so this is cancelled, so this is x by 2 for a particular values of 0, 1. So hence, so this is expected values of y given x, that is denoted as, sorry, it is not sigma, I was worried, this is mu y given x, denoted as mu y given x, this is nothing but x by 2. So it is a function of x for x belongs to, so depending upon the values of x, you can find different mean value, so that's why this is a function of x. Similarly, so it is asked in this question, find the conditional mean of x given y also. So let us find out the conditional mean of x given y. So the conditional mean, the conditional mean of x given y is equal to y is, so by definition, expected values of x given y, so this is mu of x given y. So this is by definition, this is minus infinity to plus infinity x given y, x given y. Now let us find out, this is the conditional density function in dx. So now conditional density function, y given x is 1 by x. Oh, okay. So first we have to find conditional probability density function. So the conditional probability density function, the conditional probability density function of x given y is equal to y is, first we have to find this conditional probability density function x given y, x given y. So this is joint probability density function by f of y, y. Note that this is non-zero, so this is nothing but 2 by, what is fyy? Fyy is here, fyy is 2 into 1 minus y, whenever y is between 0 and 1. This is 2 into 1 minus y, whenever, actually you have to, this is the limit, we have to write properly, x is greater than equal to y, less than 1, and y is given for a particular value of 0, 1, 0 for any other case. So here it is a function of actually x, but it is like a constant, so it is again a uniform distribution, 1 by 1 minus y in the interval y less than equal to x, given value y belongs to 0, 1, particular values of y, this will be a uniform distribution, 0 otherwise. So this is the probability density function. Hence from here we can compute the conditional mean. So this conditional mean mu, conditional mean expected values of x given y, hence the conditional mean hence the conditional mean of x given y is equal to y is mu of x given y, expected values of x given y, actually denoted by mu of x. So this is nothing but x, f of x given y dx minus me to plus infinity. Now this x given y, this density, it is between 1 and yx, this is exist, otherwise this is 0 for a particular value of y between 0 to 1. So this is y to 1, this is y to 1, then y to 1, okay, 1 to 1, sorry, this is density is 1 minus y, so x into this is x into the value is 1 by 1 minus y dx. So this is dx. So because this density exists on y to 1, and this is the multiplication with x, so it is like a constant, so it will be 1 by 1 minus y and x dx. So this is x square by 2 and limit is y to 1. So then this is 1 by 2 into 1 minus y and then 1 minus y square. So it can be written as 1 minus y, 1 plus y by 2 into 1 minus y. So this is cancelled. This is 1 plus y by 2. Now this is for any value between 0 to 1. So it is a given y between 0 to 1. This is the mean. It is also, this conditional mean also function of y. So here in this question, this variance it is not asked, but similarly we can find the variance also. Similarly we can find the conditional mean, conditional variance also. Compute the conditional mean and conditional, suppose conditional mean, both the conditional mean it is asked, so we can find the conditional variance also. So this conditional variance formula, suppose you want to find the conditional variance, because for discrete cases we computed, so sigma square, suppose we want to find a particular values, suppose x is between 0 to 1, suppose x is, it is given 0.5 and it is asked that find the conditional variance of y given x equal to 0.5. So if you want to find this, so by definition the conditional variance is given by variance of y given 0.5. This is sigma square y given 0.5, which is nothing but, by definition, this is expected values of the expected values of y minus mu of y given 0.5 whole square. So this value mu y given 0.5 we will find from here. So we have already computed. This is 1, x will be 0.5 means 1 by 2. So suppose x is here 0.5, this is nothing but 1 by 2. So expected values of y given 0.5, which is equal to mu of y given 0.5, which is nothing but 0.5 by 2. So this is 1 by 4, 0.25. So this value it is, we will find from here whenever if x is given 0.5. So that we can find from here. So this value it is known. So by definition this is minus mu to plus infinitive y minus mu y given 0.5 whole square f of y given x dy. Now this is little difficult to compute, so we will follow this formula. Y square given 0.5 minus expected values of y given 0.5, this is 0.25 we computed just now, we will take the whole square. Now what is this value? This value we have to compute now. So this value, where expected values of y square given 0.5 is defined by minus infinity to plus infinitive y square f of y given x dy. So this x here replaced by 0.5. So now 0.5 dy. Now this y given 0.5 from where we will get? So we will get here this is y given x, expected values of y. So this is the probability density function y given x. So whenever it is x is 0.5, so then it is nothing but, if x is equal to suppose 0.5, then f of this probability density function f of y given x given 0.5, we will get nothing but 1 by x, 1 by 0.5. So this is nothing but 2. So let us write down 1 by 0.5 whenever 0 less than equal to y, 0 less than y less than equal to 0 is equal to 0.5. This is 0 otherwise. So this is the probability density function. So now we'll use this probability density function. So we can write a simplified form. This is 2 whenever 0 less than y less than equal to half, 0 otherwise. So now we'll use this density function here to computing these things. So this is nothing but, so this density is non-zero whenever y between 0 to half. So that's why we will write 0 to half, then y square, and then y given x, y given 0.5. In this region this become 2, and then y dy. So this is nothing but 2 into y square, integration will be y cube by 3, y cube by 3, y square, y cube by 3, and then integration 0 to half. So this limit is 0 to half. So this become 1 by 2 cube. So this is 2 by 3 into 1 by 2 cube minus 0. So the 0. So then it is 2 to this is 1 by 2 into 4, and 2 on 2 it is cancelled. So 4 into 3, 12. So this is 1 by 12. So this is coming 1 by 12. So hence variance of y given 0.5, what we'll find. So hence variance of y given 0.5, this is equal to sigma square y given 0.5. what we found, expected values of y square given 0.5 minus expected values of y given 0.5 whole square. So now this is y square given 0.5 is 1 by 12, 1 by 12 minus y given 0.5 is expected values of y given 0.5 we computed. This is the, I think, where we computed expected values of y given 0.5. Oh, we did not compute y given 0. Here y given 0.5, it is 0.25, 1 by 4. So this is nothing but 1 by 4 whole square. So 1 by 12 minus 1 by 16. Yeah, 1 by 16. So this is I think this 24, no, 48. So this is 1 by 48. So this is the conditional variance of y given x equal to 0.5. So if this kind of problems are given, then we have to solve this problem in this way. So how to find conditional mean and conditional variance for a bivariate continuous random variable. For one random variable y and x, one random variable values are given, some value given. So conditional mean of x given y is equal to some value y, or conditional mean of x given conditional some conditional y given x equal to some value x, and conditional mean of y given conditional x given some y value, sorry. So x and y, suppose one value given, suppose conditional mean of y given x equal to x, or conditional mean of x given y is equal to y, we can find, and also the respective variances also we can find. So hope you have understood clearly. So we completed some important topics for bivariate random variables. We discussed their joint probability mass function, when they will be independent, joint probability density function, also when they will be independent, conditional probability mass function, conditional probability density function, and conditional mean and variances for discrete and continuous cases.